Today, we're going to track an invisible spy on a life-saving mission. We're talking about a radioactive element called Indium-111. We're going to see how scientists actually create this element, give it a super clever disguise, and then send it deep inside the human body to hunt down disease.
So let's kick things off with a puzzle that doctors have to solve all the time. How do you find something you literally can't see? You know, a hidden infection, a super tiny tumor. These things are mysteries locked deep inside us. How do you possibly solve that puzzle without having to do surgery?
Well, the answer is just so elegant. You send in a guide, a tiny radioactive guide that sends out a signal, kind of like a beacon shining in the dark. And by following that signal from outside the body, doctors can figure out the exact location of the problem. And for us today, our guide is Indium-111.
All right, so let's get into the mission specifics. You see, every one of these tracers has a particular job to do. And Indium-111, well, it's a real specialist. It's designed from the ground up to work with a super powerful imaging technology called SPECT. This table here shows us exactly why Indium-111 is the perfect tool for the job. See that key feature? Primary emission gamma rays. You can think of these as tiny, harmless little flashes of light that can travel right through our body's tissues. And that signal, that's precisely what the special camera in a SPECT scanner is built to see.
So what in the world is SPECT? I know, it's a mouthful. It stands for Single Photon Emission Computed Tomography. But the easy way to think about it is like a super sensitive camera. It's designed to detect those individual gamma rays. Those are the single photons that are coming from our little Indium-111 spy. By mapping out all those tiny signals, a computer can build this incredibly detailed 3D image of what's going on inside you.
So where does this special isotope even come from? It's not like you can just dig Indium-111 out of the ground. No way. It has to be custom-made for its medical mission, and it's all done inside this massive machine called a cyclotron.
Honestly, the whole process is like a form of high-tech alchemy. It's amazing. As you can see here, scientists start with a stable element, cadmium, and they put it inside a particle accelerator. Then, step 2, they just bombard it with a beam of high-energy protons. This collision sets off a nuclear reaction, and it literally transforms one element into another. Cadmium becomes Indium-111. It's just an incredibly precise way to forge an essential medical tool.
Now, here's the thing. Just creating Indium-111 isn't enough. If you were to inject it on its own, it would just kind of wander aimlessly through the body. To get it to go to the right place, it needs a disguise, a chemical partner that acts as its guide, leading it with pinpoint precision right to its biological target. And this is where the magic of radiopharmaceutical chemistry really comes into play. The key is this molecule called a bifunctional chelator. I know it's a tricky name, but just think of it as a smart, two-sided clamp. One side is designed to grab onto that Indium-111 atom and just hold it tight, making sure it doesn't break free. The other side is designed to attach to a very specific targeting molecule, like an antibody or a peptide. And here you can see the final assembly. You've got the Indium-111 atom, which provides the signal. You've got the chelator, which is that essential link in the middle. And then you have the targeting molecule, which is basically the homing device. You put them all together, and what do you get? A precision-guided radiopharmaceutical, all ready for its mission.
So, now that our tracer is all put together and ready for its mission, let's look at what it actually does. What kind of critical medical questions can Indium-111 help us answer?
Well, the applications are incredibly diverse and absolutely vital. For example, doctors can take a patient's own white blood cells, tag them with Indium-111, and then re-inject them. Those tagged cells then act like tiny little detectives, heading straight to any hidden infection. For cancer, the tracer can be attached to an antibody that hunts for prostate cancer cells or to a molecule that locks onto neuroendocrine tumors, basically making them light up on a scan. But here's the part that's a real game changer. This isn't just about diagnosis. By confirming that a target is there, Indium-111 helps doctors plan for future treatments. It's a revolutionary idea called theranostics, where you first see the target and then you treat the target.
This quote really puts the whole journey into perspective, right? The success of tracers like Indium-111 is what drives the science forward, pushing us to create even more sophisticated tools for seeing inside the human body and ultimately fighting disease. And all of this leads to one incredible forward-looking question. We figured out how to use these atomic guides to find disease. So what's next? The frontier is now arming these guides, using similar isotopes to deliver a payload of radiation that doesn't just find the target, but destroys it.
I mean, just imagine a world where medicine isn't just diagnostic, but it's a precision-guided strike against disease, all led by these tiny invisible beacons.